Hey everyone, and welcome to this explainer. Today, we are diving into an absolute thriller of a cosmic detective story. We're going to be looking at worlds located literally light years away from Earth, places so incredibly hostile and extreme that they are challenging everything we thought we knew about planetary physics. What starts out as a pretty straightforward investigation into extreme weather on distant planets actually ends up revealing massive, invisible forces at work in the deep universe. By the end of this explainer, you'll see how a bizarre atmospheric mystery has given astronomers the strongest population-wide evidence yet for magnetic fields on exoplanets. It's a total game changer, and it could fundamentally shift how we search for alien life in the future. So, let's just get right into the evidence. Look at this number, 15,000. We are talking about wind speeds measured on planets light years away that are blasting at more than 15,000 miles per hour. That's roughly 25,000 kilometers per hour. Just to put that into perspective, that is profoundly faster than anything we've ever observed in our own solar system. Even the most violent, raging storms on our own Jupiter don't even come close to this level of atmospheric fury. This mind-boggling wind speed is the initial clue in our mystery. But to really understand why these winds are happening and why they completely baffled scientists, we first need to establish exactly where in the galaxy this cosmic crime scene is located. So, to understand this mystery, we have to zoom way out, well beyond our solar system. Astronomers have discovered thousands of exoplanets since 1992, and they range from these little rocky super-Earths all the way to massive deep ocean worlds. And each new discovery gives scientists just another puzzle piece to understand how planetary systems form and evolve over time. But the specific exoplanets we are focusing on today, well, they belong to a very special, extremely violent category. Enter the hot Jupiter. And yeah, the name pretty much says it all. Unlike our own Jupiter, which sits comfortably far from the sun in a deep freeze, these massive gas giants are parked dangerously close to their parent stars. Blasted by relentless stellar radiation, their environments are, frankly, hellish, with temperatures easily exceeding thousands of degrees Celsius. And it's exactly this proximity to their star that sets the stage for our 15,000 mile-per-hour winds. Because these hot Jupiters orbit so tightly, many of them are what we call tidally locked. Basically, one side permanently faces the star in scorching heat, while the other side is permanently trapped in freezing darkness. And this brilliantly illustrates the core problem. This massive planetary-scale temperature contrast forces the planet to try and balance itself out. It triggers these violent planet-wide winds that just whip around the globe, frantically trying to transport heat from the boiling day side over to the freezing night side. Now, you might be wondering, how exactly did astronomers measure a breeze on a planet that is literally trillions of miles away? Well, the investigation relied on some seriously powerful observatories, specifically the Very Large Telescope and the Gemini North Telescope, using a technique called advanced spectroscopy. Here's how it works. When light from the host star passes through the exoplanet's atmosphere, certain wavelengths of that light get absorbed by the gases there. But because those massive winds are violently churning the atmosphere, the physical motion actually shifts those absorbed wavelengths. By calculating those exact shifts, scientists were able to measure wind speeds ranging from about 4,470 miles per hour all the way up to over 15,500 miles per hour across 7 different hot Jupiters. Going into this study, the scientific community had a very logical assumption, totally based on the fundamental laws of thermodynamics. The equation is incredibly simple. More heat equals more energy, which equals faster winds, right? When a planet gets more energy from its star, the atmospheric gases heat up and they expand. This expansion creates massive pressure differences across the planet, and those pressure differences are exactly what drive the winds. Therefore, scientists fully expected that when they finally looked at the data, the absolute hottest hot Jupiters in their sample would inevitably have the absolute fastest, most violent winds. It just makes sense. But here comes the plot twist. Now, what's really interesting about this slide is that the actual data completely contradicted all existing models. The hottest planets were supposed to have astronomically high winds, but instead, the observed winds on those scorching worlds were surprisingly sluggish compared to their cooler counterparts. This unexpected result threw a massive wrench into the investigation. The basic physics of heat and pressure hadn't magically changed, which meant something else, something huge was at play here. And that brings us to the central mystery of our explainer. I really want you to think about the sheer momentum of a planetary atmosphere moving at 15,000 miles per hour. We are talking about billions of tons of gas moving at hypersonic speeds. What invisible force out there in the cosmos is powerful enough to step in and act as a giant brake pedal on that kind of momentum? It obviously can't be a physical barrier like a mountain range. These are gas giants. No, it had to be something operating on an invisible, planetary scale. Okay, let's dive into this. The invisible culprit? It actually acts as a giant magnetic brake pedal. You see, the extreme heat on these uniquely scorching worlds partially ionizes the atmospheric gases, basically stripping away electrons. Once they're charged, these particles get completely caught up in the planet's magnetic web. This intense interaction creates massive drag, restricting the circulation and literally slamming the brakes on those hypersonic winds. It was the smoking gun astronomers were looking for. These winds were slowing down because they were crashing headfirst into magnetic fields. Just as a quick refresher, these invisible shields are generated deep within a planet by what's called a planetary dynamo. Just like on Earth or Jupiter, it requires electrically conducting material continuously churning inside the planet, driven by rotation and convection. It's essentially a giant internal cosmic generator that produces an external shield. What's honestly just remarkable here is that measuring these winds allowed researchers to indirectly measure the strength of these distant magnetic fields for the very first time. And let me tell you, these aren't weak fields. The estimates suggest they are actually stronger than some planets right here in our own solar system. Though, to be fair, they're still a bit weaker than our own Jupiter's massive field. But this data represents a huge leap forward. It's the first robust estimate for an entire group of exoplanets. But taking a step back from the pure physics for a second, this discovery paints a frankly breathtaking visual picture. If these towering gas giants possess strong magnetic fields that are catching charged particles, they are likely producing a spectacular galactic light show. When charged particles are funneled by magnetic fields and collide with atmospheric gases, they emit light. We see this on Earth all the time as the northern and southern lights. But on these extreme hot Jupiters, the resulting alien auroras would be fueled by vastly more energy. These displays could very well be among the brightest, most intense auroras in the entire galaxy, permanently lighting up their alien skies. Now, while giant alien auroras are incredibly cool to imagine, let's pivot back to why finding exoplanet magnetic fields is so fundamentally important to us back on Earth. It really all comes down to planetary survival. A planet with a magnetic shield can deflect harmful solar particles and radiation, which in turn protects and preserves its atmosphere. On the flip side, a planet without a shield is sitting completely vulnerable. It faces extreme radiation exposure, which can strip away its atmosphere over time and completely boil off any potential liquid water. Earth's magnetosphere is precisely what makes our planet hospitable. So, the crucial point is that magnetic fields are intimately tied to the search for extraterrestrial life. Life, as we currently understand it anyway, requires a very specific checklist of essential conditions: a stable atmosphere, a suitable temperature, liquid water, and most importantly, long-term environmental stability over billions of years. Magnetic fields act as the invisible guardians of that checklist. Without them, stellar winds would strip a planet bare long before complex life could ever evolve. And that is exactly why detecting them is an absolute holy grail for astronomers today. Which leaves us with this final, pretty provocative thought to chew on. The hot Jupiters we discussed today are far too hostile and violently hot to ever support life. But the sheer brilliance of this discovery isn't actually about these gas giants. It's about the method itself. By using atmospheric winds as a natural detector for magnetic activity, scientists have proven that we can find these invisible shields across the vastness of space. As upcoming next-generation telescopes and instruments come online, researchers are going to apply this exact same technique to rocky, Earth-like exoplanets. The invisible forces hitting the brakes on 15,000-mile-per-hour winds today, well, they might just be the exact same forces that guide humanity to a sheltered, habitable new world tomorrow. Thank you so much for joining me for this explainer, and as always, keep your eyes on the stars.